Welcome back, everybody. Now, today we are going to spend a little bit more time on these optimization algorithms. And we will also jump a little bit back and forth between the lectures from last week, and especially when it comes to the implementation of the calculation of gradients. So just to remind you of that. And then we are going to look at some of these algorithms, although when you use these algorithms, you will essentially use these canned algorithms like the Broyden's algorithm, or you can use the Broyden. It's actually Fletcher Goldberg channel, so it's not Farberg, it's Fletcher. So I always make an error with the names of these. And then you have methods like Powell methods, etc. And these are all popular methods which you can use in particular in project one, since we only have very few parameters, actually only one variational parameter. And that makes it easier to actually use these methods. But I wanted to give you a kind of idea of what is behind these methods. But when it comes to actual implementations, you will just use, let's say, scientific Python or scientific libraries if you're programming in C++ or Fortran. Then you have libraries where you can actually implement these methods efficiently. But if you implement these methods, you need to provide, as we discussed last time, a function which sets up the derivative and a function which contains the function itself, which you want to optimize with respect to a given set of parameters. But then, and this is something which also overlaps with the courses which some of you may have taken on machine learning, because in machine learning, I mean, these different gradient methods are widely used because you have a multi-dimensional object you want to optimize. Now, one of the possible paths for project 2 is to replace the trial wave function, which you're setting up here, with a neural network. And that is something which has been shown to be extremely powerful. And when you do the optimization, then you will have many more parameters to deal with. And that is one possible path for project 2. And in that particular case, you end up with a function with many more parameters. So this will be the parameters of a neural network. And in that case, the energy itself is a function of many parameters. This can typically be in the tens to the hundreds of thousands. And then you would need methods like stochastic gradient descents and different variants. So this is something which is useful to have seen, even if you don't use it. Now, for those of you who have followed courses in machine learning, this is something which is a kind of basic algorithms. So I'm just going to give you a kind of overview here only. And then there's a final point about automatic differentiation, which is also very useful, especially when we now change the trial wave function. Because as you probably have seen, to do this by paper and pencil is actually pretty boring and time consuming, and it's easy to make errors. Now, one thing you can do is to do an approximative calculation of the second derivatives for the kinetic energy and the gradients using finite difference formula. But that gives you often results which depend on your step size and can be less precise. And that's where automatic differentiation comes in. So let's just move on a little bit here. And I'm going to give you a quick reminder of Newton's method, as we discussed before. So this is just a Taylor expansion around the point S. And we want to find the roots of that function. And in that particular case, what we do when we do the Taylor expansion is that we get an expansion like this. And at the end, we end up with an algorithm, which this is what we discussed last time. Now, in our case, the function which we want to find the roots of is the gradient. So that means that we have a first derivative here, and then we have a second derivative here. And the actual function then, so in our case, f is the gradient of the energy, and this is the so-called Jacobian matrix. And you can quickly see that. So I'm just going to skip some of these details, but you can quickly see that if you have a function of two variables, because then you need to calculate a gradient, and you need these higher derivatives. And it means that the function which you need to invert in that case is actually for function f of x. This is then the first derivatives with respect to the different variables, and it's normally called the Jacobian. So what you end up with is an algorithm where this quantity here means that you have to invert a matrix. Now, in our case, the function which we want to, as I said, the function we want to calculate the roots of is the gradient. So that means that this is a second derivative. And the more parameters you have, the more involved this function becomes. So many of these methods, these quasi-Newton methods, they start with this type of approach, but they change the way you evaluate the second derivative so that you don't need to evaluate this matrix, which has to be inverted. So this is a 2x2 matrix. If you have two, you could now think of the x's as two variables, two variational parameters, alpha 1 and alpha 2. If you now deal with a neural network as your trial wave function, then this matrix can have a dimension of 100,000 times 100,000. And to calculate these derivatives is something you don't want to when it comes to Monte Carlo calculations, because these derivatives then involve many integrals, which you have to evaluate stochastically. So calculating these derivatives is not an easy thing. So you need to compute the inverse of the Jacobian matrix. And it is this case which actually gives a lot of difficulties in the calculations. So I'm going to skip some of the things here, because these are things which we discussed a little bit earlier. This is about convex equations. But I wanted to mention the basics of Broyden's algorithm and the algorithm which is called Broyden, Fletcher, Goldberg, and Shano, which is one of these, workhorses for optimization problems, where you avoid calculating the Hessian matrix, or the matrix which you have to invert. So Broyden's method is actually the first entry point. And unlike Newton's method, which requires the combination of the Jacobians at each iteration, Broyden's method approximates a Jacobian to reduce computational cost. And the way it does it is to introduce what's called the second method. So I'm just going to explain some of these details. So what we want is solve this type of equations, an f of x equal to 0. And the goal is actually to find this x so that this f of x is equal to 0. That's essentially what we want. So Newton's method, in the general case, gives us this Jacobian matrix, which we have to evaluate. And we don't want to do that. So Broyden's method, there are actually many approaches. There's the bad one and the good one. And I will try to explain which one. But normally you would not use Broyden's method. Broyden's method is actually a method you can implement easily yourself, like the gradient descent, which we discussed last week and the week before. So this updates an approximation of Jacobian matrix, and this updates an approximation of the inverse Jacobian matrix. So the good method, so what we do now is that we make an approximation of the Jacobian at a given iteration. So that means what we are doing now is that we are calculating the difference. So these are the finite differences here. And these finite differences, if you now think of the second equation, so the second equation is actually this one, where this equation here contains the function, and then this s of k in its first, as you can see, s of k here. So if we just switch to the whiteboard, just let me remind you of the second method. So let's just stop sharing here and go back to the whiteboard. So if you look at the second method, which is a basic building stone in Broyden's method. And Broyden's method becomes a stepping stone towards the more advanced one, the Broyden, Farberg, Fletcher, etc. So the second method is a very simple way where you calculate the derivative. So derivative is approximated so you have f, and this is a derivative, so this is f prime, and the derivative calculated at point x of k. This is normally given by a function f(x) of k minus f(x) of k minus 1, divided by x of k minus x of k minus 1. So this is the first step in Broyden's method. And that means that when we now look at Newton's method, so back to, if you now go back to Newton's method, what you see now is that you can, since we now have x of k, so this is the point x of k plus 1, and this is x of k, then we can rewrite that one as f(x) of k, and this is multiplied with the derivative of x of k. So now I'm not using the gradient of the energy. So in our case, remember now that this function is actually del with respect to some parameters, and this is the expectation value of the energy as a function of alpha. So now I'm just setting up Newton's method as it is computed normally. And now with the second approximation, what we have then is x of k plus 1 is equal to x of k minus f of x of k. And this is then multiplied with the x of k minus x of k minus 1 divided by f of x of k minus f of x of k minus 1. So what I'm doing now, I'm simply plugging in the second here. So Broyden's algorithm is an algorithm where you now replace the calculation of the Jacobian with this simpler approximation to the derivative. So what we have then is that it's normal not to invert, but rather to solve. So this function which you have, the way we have written it, if you now think back to the way we wrote the algorithm, so in principle, Newton's method, if we just rewrite it, is then given by x of k plus 1 is equal to x of k minus, and then we have this Jacobian, which is inverted, calculated at x of k, multiplied with f x of k. So it's normal not to invert that equation. So normal not to invert, because this can be a matrix of huge dimensionalities, not to invert, but to solve a new equation for j, where we have j x of k multiplied with some vector s of k, which is then equal to minus f of x of k. Now just keep in mind that what we are setting up is x of k plus 1 is equal to x of k minus j minus of f(x) of k. So that means that what we have then is that we have an x of k plus 1 is equal to x of k plus this x of k. So this is just till now just manipulations. Now the algorithm now is to define some initial x0 and some initial Jacobian b0. And then when you have that, so the basic algorithm here is actually pretty simple. So first we define some initial point, initial guess. And the initial Jacobian. And the way you would calculate this initial Jacobian is to use this second formula, which we set up earlier here. And let's just call this B0. And then the type of algorithm which you would set up then is as follows. So then you would then, for K equals 0 to the number of iterations, max iterations. So you need to set that up. Then we would simply solve an equation of the type B of K. So we start with an initial value. We have defined S of K, which is minus F of X of K. Then we update X of K plus 1, which is equal to X of K plus S of K. This Y of K, we define that intermediate quantity, is simply X of K plus 1 minus F of X of K. And that means that we can now set up the next iteration as the previous value, B of K, plus, and then we have Y of K minus this BK, X of K, and this is multiplied because these have to be set up as variables which are scalars, and this would just give us the end of the for loop. And then finally, we have BK S of K is equal to minus F of X of K for the final iteration here. So the typical way by which you would solve this, since you don't want to invert that type of equations, is that we use the second method. So typically now you need a guess for these. So let me just say that one, not that one. This one. Okay, let's just go back to the slides, and let me just set that up again. So the equations which we are setting up when we implement Broyden's method is then a type of equation where we use the second equation to perform this update. And then the solution is updated like this. Then, so this is a good method. Now in the bad method, we let H of K be an approximation of the inverse Jacobian. And then the update rule is given by this equation, which I put up. But that means that we have to calculate this function H of K, which can be problematic. So this is actually the inverse second equation. And then the solution is updated like this. So you use the second equation to find an approximation to the derivative. And then you have an update rule. So essentially, the way it moves is that you, a good method, you initialize x0 and this b0. And in many, many cases, people actually approximate the gradient by setting it equal to the identity matrix. That's a pretty common approximation. Some people even set it to some random values. And then you run through the different iterations. You compute this step, S of K, which is BK minus times the value of the function. You update the solution with the X of K. Then you compute this element for the second method. And then you update the Jacobian approximation simply by having this B of K plus 1 is equal to B of K, because then you find the new B of K. So in the next iteration, you plug in that value, and then you keep going till the root which you're searching for is less than or equal a specific step size or value which you have decided. So that is the basic approximation which is used. And the standard approximation is actually to use the second rule, as we said. or the second equation, which simply takes this right-hand side, which you have here, and divide it by x of k plus 1 minus x of k. So you see now that the b of k plus 1, if I divide with s of k, that is simply my derivative where I use a what is normally called a second approximation, or this could just be a one-step forward algorithm. So you're approximating the derivative with just these finite differences. And the whole idea then is, since s of k, if you, as I said, if you divide with s of k here, you have nothing but the standard second approximation to the derivative. And then you keep updating. So your new value is b of k plus 1 is equal to this expression here, and then you plug it in so that you end up with an equation where you have a set of these types of equations here, and then you keep updating, and then till you have reached this convergence. So this is Broyden's original method. Now this was improved by introducing the Broyden, Fletcher, Farberg, Goldberg, Shano method. And if we just stay with this method here, it avoids to compute the exact Jacobian at each iteration. And it's normally suitable for high dimensional problems where computing the Jacobian is expensive. For us, even if we can compute the Jacobian, that is going to involve many Monte Carlo integrals. And for us, it's going to be extremely expensive to calculate. And that's why we end up with these more approximative methods, like Broyden's method. One of the problems is that convergence is not guaranteed for all problems. And also the approximation of the Jacobian may become inaccurate over time. We require many reinitializations. So one method, which we are going to look at now, is the Broyden, Fletcher, etc. So Broyden method is easy to implement. It's actually used in optimization problems. So if you go into scientific Python, like we discussed last week, and this is a function I recommend you use when you're finding the roots of the gradient. When you use scientific Python, you will see that Broyden's method is a possibility. And it's actually used a lot in optimization problems and also for machine learning training. The Fletcher, Gold-Broyden, etc. Is a method which gives often fewer iterations to reach the minima. And it's one of the more favorite methods in these kind of optimizations where your dimensionality of your matrix is not that large. So this is another point which comes into play. If we just spool back a little bit and look at the calculation of the Jacobian here, even if you can calculate it with these methods, if you now are dealing with, let's say, more than 10,000 variables which you want to optimize, the matrix here becomes a 10,000 times a 10,000 matrix. And this is something you don't want to deal with. Even if you have an approximation like Broyden's method or the more advanced methods, which give you then a estimate of the Hessian, the second derivative, or here the first derivative, even then it's actually such a multi-dimensional problem that you simply don't want to invert the matrix. And if you deal with a neural network, 10,000 parameters is actually a very small neural network. So you would typically have millions of parameters. And that's why these methods, they are okay if you have something up to, let's say, 10 to 100 parameters, then they are easy to run and they often work pretty well. But if you go to more multidimensional problems, these are not the methods. And this applies to the BFGS as well. So this is also an iterative method to update the Hessian, but it's slightly different from Broyden's method. So the optimization here is to optimize f of x, where that is a vector as before. And the typical approach here is that you find a search direction at a given stage, which is given by the solution of the analog Newton equation. And this looks very much like what we put up for Broyden's method. And this B of k is an approximation to the Hessian matrix. And in our case, we call this an S of k. So what you do then is to use a gradient of the function evaluate a given value x, and then you have a line search in a direction of one of these direction, and that's used to find the next point. So let me just move on a little bit. So what we end up with then, so we are giving the following unconstrained optimization problem, and then the first order necessary conditions for optimality are given by the gradient being equal to 0, where delta f of x is the gradient, obviously. So the typical recipe here, oops, went a little bit fast here. Let me just escape, take it out of the full screen. So the is an iterative procedure that approximates the inverse Hessian at each iteration. So you would typically again initialize and choose an initial guess for the inverse Hessian, typically again the identity matrix. And then you would compute the gradient at the current point. You compute the search direction where you have this guess. So in the first iteration, this is just the identity multiplied with this quantity. Then you perform a line search to find an appropriate step size, alpha k, which minimizes this function. And then you update the current point with this standard recipe which you have here. Then you compute the gradient. And when you computed the gradient, then you update the inverse Hessian approximation where you use, again, the standard formula which you had from the second method. So this is, again, playing around with much of the same equations. And you see now that if I take this quantity here and divide by this one, that gives me an estimate of the derivatives. So that gives an estimate of the Hessian matrix, which we now can rewrite in a more compact way like this. But this means that we have to compute this quantity which you see here. And then you would repeat this process until convergence. That means that until this quantity is sufficiently small. This is essentially the basics of the BFGS method, which we applied last week. Now, for us, this is a method which I would typically recommend using in Project 1, together with eventually just a simple gradient descent. So let me go a little bit back to what we did last week. So in last week, we implemented actually this algorithm, but we also implemented a standard gradient descent. So this method is normally guaranteed to converge a local minimum, such as the objective function being smooth and convex. We are pretty happy in our case, or lucky, because we have a function like the energy, which is a convex function in terms of the variable we want to optimize. So in most of the applications we are going to see in this course, the function we want to optimize has a global minimum, and it is a smooth and convex function. And you've already seen that when you calculate for the harmonic oscillator, your energy function is a very nice smooth function of the parameters alpha. So the properties, you don't need to calculate second derivatives. So it approximates the Hessian matrix. It has something which is called superlinear convergence. So typically converges faster than gradient descent methods, especially when you're close to the optimum. But that also tells you that you have to be a little bit careful with your initial values. And it's pretty memory efficient because it maintains a low rank approximation of the Hessian matrix. So it becomes computational efficient. Also, the Hessian matrix, which we are looking at, is a positive definite matrix. So the eigenvalues for the energy, the function which we are optimizing, we will get a second derivative, which is positive definite. Actually, this second derivative is proportional to the variance of the problem we are looking at. And the variance is always larger or equal to 0. So these methods are widely popular. Feel free to use them, especially in project number 1. If you continue with, let's say, the fermionic case in project number 2, where the only thing you need to do is to change the trial wave function for the bosons with a Fermi Slater determinant, then you can actually still run with these methods here in the optimization part. So it's an effective and widely used method. And this is actually the one I would typically recommend that you end up using. After we've looked at the programs, we are going to look at again, the steepest descent method, which is a stepping stone, the first stepping stone towards the conjugate gradient method. Now, we are not going to implement the steepest descent because that requires that we calculate the second derivative of the energy. That means the Jacobian matrix. And that is going to involve, if you think the gradient is involved enough, then the second derivative contains 6 to 7 integrals, which we have to evaluate stochastically. So typically, we will not use these methods, but I'm going to mention the steepest descent just for the sake of completeness. So let's go a little bit back to what we did last week. So let's go back to the notes from last week. And I wanted to bring up the code which we had. So let's now bring up the code here. So the program which we have, as an example in the lecture notes, I'm using this 2-electron case. And in the 2-electron case, let me just run this part here. What I'm doing first here is to set up the, if we go back, we have the trial wave function, which also includes a correlated part. It has a local energy where I'm actually able to calculate the analytical expression for the local energy with this specific trial function. But this is where you, when you need the second derivative, where you can use automatic differentiation. Here I actually set up the ansatz for the derivatives because I need a derivative with respect to the parameters alpha and beta. Then in my Monte Carlo approach, what I'm doing now is to evaluate these 3 integrals, which we discussed last week. So I just wanted to refresh that. And what we have here is a derivative of the trial wave function. And then we have the energy derivatives. And we also need to calculate the energy. So we run through the Monte Carlo cycles. We have importance sampling baked in. And then we calculate the ingredients needed for the 3 integrals. So we have the derivative of the wave function multiplied with the energy, so which is given by this term. That's one of the integrals. We have the derivative of the wave function itself, which gives another integral. And then you have the energy itself. And the final energy derivative is given by this formula, which we derived last week, which is a derivative of the wave function multiplied with the energy, that expectation value, minus these expectation values here. So what we have is actually 3 integrals, which we need to evaluate. And here we run it for 2 particles. And in this particular case, what you see now is I'm just setting up blindly 50 iterations. I play around with a learning rate, as we call it, which replaces my Jacobian matrix. So this quantity here becomes a parameter. And it's pretty common, since these calculations can be faster than a calculation where you evaluate the Jacobian matrix. It's pretty common then to just play around with different values for eta and pick the optimal one. This leads also to so-called optimization methods, which you find from or inspired from the machine learning literature. So it means that when we now look at the gradients with respect to the parameter alpha and the parameter beta, then we can simply calculate these by multiplying with eta. And that's the new update of the parameters. And you see now that in this specific case, since we have a harmonic oscillator, and for a system which has a very strong harmonic oscillator frequency, the harmonic oscillator dominates. And we get a parameter alpha, which is close to 1, where we have the minimum, as you've seen also in project number 1. And this is the optimal value for beta. And you see also that the derivatives after, as we discussed last time, after 50 iterations, and not exactly zero. This energy is actually pretty good because this is a case where we have an analytical result where the energy should be 3.0 exactly. But you see, you get a pretty decent result. And this was only with something like 10,000 iterations here. Now then, so this is just us implementing a plain gradient descent. But then we have the same case with Royden's algorithm in scientific Python. What you have to be careful with here is that you need a function which calculates the derivative. So in this function here, I just calculated energies and derivatives. But here I've split it into two functions as we discussed last time. One which sets up the energy, which you have here, the energy derivative, and then a function then which also calculates the energy. So this is actually a pretty brute force program. So you have the energy and the energy derivative. And this is because this algorithm, which we have here, this is the way you would call it with scientific Python, the BFGS. If you want to use Powell's method, you just replace it with Powell. If you use Broyden, you just replace it with Broyden. And there are many other methods which you can implement. So I would typically recommend using this method for project number one. But you should also play around with, if you have time, with your own gradient descent. You will see that the gradient descent is going to be sensitive to the value of the initial values and also the learning rate. In this case, we also run this with 10,000 iterations, Monte Carlo cycles 10,000. You will see that next week, when we start discussing how to calculate the standard deviation correctly, because all these results have a standard deviation. And next week, we're going to implement a statistical method for evaluating correctly the standard deviation so that we can have 2.99 plus minus something. Now, what we are going to do next week with these programs, so you're going to see them again next week. We are going to run the calculation till we find these optimal values with few iterations. So the whole idea, as you see here, is that we use something like 10,000 points or Monte Carlo samples, which then are meant to give us an estimate of the optimal parameters here. And then with this estimate, we start the big Monte Carlo machinery. So that's essentially what we will be doing next week when we look at a statistical analysis of the data which we get. Because now we are just spitting out the expectation value of the energy, but we've been pretty careless about the calculations of the standard deviation. So any Monte Carlo calculation, since this is a stochastic calculation, has to be accompanied by an evaluation of the error, which in our case is a standard deviation. So that means we need to calculate the variance, and then we do the standard deviation, and then we have the final result, which will be then 2.99 something plus minus something. So this is the topic more for next week. Okay, so what I wanted to say a little bit about is also the so-called steepest descent method, and then we take a break, and then we make a summary of these optimization methods and look more at stochastic methods, which can be relevant for project 2 in case you want to study neural networks, which replace the trial wave function. So just to say a little bit about that, now you have a trial wave function which you plug in. With a neural network, you can actually replace that trial wave function with a neural network and then perform the same optimization path as before. Any questions to this basic recipe which we need to implement? So as I said, you can choose which one of these methods. And if you wish to attempt a gradient descent method, this is just a plain gradient descent, feel free to do that as well. But for project 1, I would typically recommend using some of these methods like Powell's method, Broyden's method, or just the BFGS. Okay, so we are going to go back to the notes from this week. And I wanted to say something about the steepest descent method, which is also a very popular method. So the steepest descent is a stepping stone towards the conjugate gradient methods, which is one of the standard methods for finding solutions of problems. But then, so what we are starting with is a function of this type. So this is the function which we want to optimize. So if you then take the derivative of this function here with respect to vector x, if you take that derivative, and this is what we want the gradient to be 0, right? So think of P of x here as your energy. And then we take the derivative of that one, and then we end up with a problem like that. So this is a standard linear algebra problem where we have a known vector here, the unknown quantity here, and a known matrix A. So in principle, you could actually just invert the matrix and then you have X. But that's not the most efficient way of doing that, because matrix inversion requires, if the matrix has dimensionality n times n, it requires n cubed floating point operations. And you would like to avoid that. And also in many, many cases, these matrices can have simpler forms. They can, for instance, be tri-diagonal, which then allows for much simpler algorithms. But the steepest descent, the way it works is actually that you start with some initial guess and you consider this system, and from this system you define a residual. So if you now look at the equation which we have, so you want to optimize this problem, this is the same as solving this problem, because taking the derivative with respect to x gives this equation here. And then you start with a guess of x0. And x0 can sometimes just be 1, or it can even be 0. Because then, if x0 is 0, then what we have is that in that case, things are much, much simpler, actually. So the way you do it is that you compute the residual, that is the error you make. So if you have the exact value, x of k, then this r of k is exactly equal to 0. So this is when you terminate the iteration. So if you look at this equation here, you can manipulate it, and you get a b, which is simply a times x of k, plus this parameter alpha, which we can determine. And we can rewrite this one in terms of b minus a of x of k. And what we want now is the case where rk plus 1 is 0. Because that's when we terminate. This is just the error you make. If you have the exact solution x, then a times x is equal to b. So this just measures the error you have, because you would typically start with an iteration here. If you then set up the equations, this is what you end up with for this parameter alpha. And that means that you get an iterative recipe where x of k is updated with this parameter, which is actually the learning rate. So this r of k plays also the same role as the gradient, which we have in our equations. But you see now, here, you need actually to evaluate the inner product of the gradient. So r of k is the same as the gradient in our case. And you also need to evaluate the Hessian matrix, A, which in our case is going to be the second derivative of the energy. So if you can evaluate these terms easily, then the steepest descent is a very efficient method. And it forms a kind of a stepping stone towards the conjugate gradient methods, which is a more efficient set of methods for finding the roots of these equations. So all of these equations actually start with something like this. And if you think back to where we started when we derived Newton's method, we actually ended up with a Taylor expansion of our function, where this term represented the first derivative term, And this term here represented the second derivative term. So this is pretty similar to what we got when we did the Taylor expansion of the energy and we stopped at the second derivative. Because the Hessian matrix A, which you have here, is nothing but the second derivative of the energy in our case. So this type of equations, as you can see, there are tons of methods. And I guess there's still place for your name somewhere here if you can cook up a new method. So what I wanted to say is that when we are dealing with this low dimensional or few parameters, I would recommend using Broyden's method or the BFGS method in project 1. Alternatively, you can write your own gradient descent. I do not recommend using the steepest descent or the conjugate gradient descent methods, because all these methods require, when you do the iterations, require that you can evaluate the second derivative. In our case, the second derivative is a time-consuming sink. It's actually a place where you are going to, if you want to calculate it, it's going to involve 6 to 7 integrals, depending on how you do it. And doing that stochastically with many dimensions, it's just going to be almost a waste of CPU cycles. When you have methods like Broyden's method or simpler gradient descent methods. So after the break, we are going to summarize a little bit about these gradient methods and their limitations. And then we will just look at some additional methods. And this will conclude the optimization part, which we need in project 1, but we will also need in project 2. Any questions so far? What do you say? Should we take a small break? So what we are going to do now is to look at some of these gradient descent methods and discuss their limitations. So a typical gradient descent is a function which, or a method which finds typical minimum function. And if it converges to the local minimum of a function. In machine learning, which will be relevant for project number 2, if you want to do that. I mean, you don't need to do that, but I'm using ML here for machine learning because these are methods which are widely used in a machine learning setting. So you're often dealing with difficult functions. Now, in our case, we are pretty lucky because the energy in general is a nice, smooth function of the variables, which means often also that there is a global minimum. And in many, many cases, there's just only one minimum. So this makes life much, much easier. But you will find that it's very sensitive to the initial conditions. That's something which can actually change the way we run the calculations. And we discussed that last week in connection with us being stuck in a local minimum, or we can even be stuck in a so-called saddle point. This is something which we just illustrated last week. Now, in general, the gradients are computationally expensive to calculate. They can be very sensitive to the choices of these learning rates. And it's another thing which it does is that if you have a constant learning rate, is that the way you change in the spatial directions is the same. You change by the same rate if you have a constant learning rate. And this is, so if we now go back a little bit to many of these other methods, so if we look back at, let's say, a steepest descent, you will see now that in the steepest descent algorithm, you have the possibility to change this parameter. So this R of k is the same as your gradient. This alpha of k is what we normally call the learning rate. But for the different methods, you have a recipe by which you can update this learning rate for every iteration. For the standard gradient descent, this is not possible. And that means that often you're stuck with just one fixed value. And that means that all the gradients, they move with the same constant rate in the different directions. The gradient itself can be small, but you multiply it with the same constant. And that's something which can limit the efficiency of the search. So the fact that this actually treats all directions in parameter space uniformly is something which is actually a drawback. And it can also take an exponential time to escape saddle points, even with some random initializations. So one way to improve your gradient descent is to use something which is called momentum. Now, momentum is actually you giving a previous iteration a certain weight. So you have a kind of memory. So the name momentum comes from a rewrite of Newton's equation. But the way you can think of it is that this is nothing but you multiplying the previous iteration with a given constant. So if we go back to the Jupyter, no, to the whiteboard. So let's do that. So there is this is often seen as a kind of ad hoc method. So improving a gradient descent. And I'm using the shorthand GD for gradient descent with momentum. So if you think of the basic algorithm, so you have some parameter alpha of k plus 1, which is now being updated from the previous iteration, minus some parameter lambda of k, and then we have a function which we simply label as f. So this is essentially what we are doing now. And this is evaluated as a derivative of these parameters alpha at a value alpha of k. Now, this gamma of k here is the parameter which we called for the learning rate. Now, one way we could do this is actually to have a weight on a previous iteration. So it means that we could weight a previous iteration with a constant. With a constant value. So that means that I could now calculate an intermediate quantity where I have an alpha of k here, which actually goes over to some parameter, which I call 1 minus rho times alpha of k, plus this parameter rho times an alpha of k minus 1. So this rho becomes a parameter in the optimization part. So the reason why you do that, if you look at this equation here, if you have large fluctuations from one value of k to another value of k, so suppose your gradient varies a lot, which means that alpha of k can be quite different from alpha of k plus 1. What you can do then is that you can dampen a little bit this big variation by keeping track of the values from the previous iteration. So if your gradient goes up like this in big jumps, then what you could hope for doing by keeping track of the previous iteration is that this smoothens out the big variations in the gradient. This is a trick which is used in many algorithms. So if you go to Hartree-Fock methods in many-body physics, this is actually used in order to alleviate convergence problems in Hartree-Fock calculations. So this kind of trick is a widely used trick, and you will see now from the simple examples which we have online that this is actually going to speed up the calculation of a derivative. So let me just bring back then the Jupyter notebook, and you will see that in one of these examples here. So in this example, and I hope you don't get offended, the function which we are evaluating is just x squared. So that means that the derivative is obviously 2 times x, okay? In this particular case, I'm setting up my gradient descent, and I run through the gradient descent. So the gradient is the derivative of the solution. I set up my gradient descent algorithm. So that means that when I run the calculations now, what I'm doing with the gradient descent, you see now that in this case, I need something. This is just a plain gradient descent where I fixed a learning rate, the step size of 0.1. Okay. And then I give it an initial value. So I start at I want to find, I know that the minimum is between -1 and +1. And I'm giving an input value, just a starting value for X. And you see that my input value is 0.74 here. And this gives me my function value. And then at the bottom here, at roughly it's 0. X squared is 0 at 0, obviously. And you see now that after 30 iterations here, or 29 here, I'm actually getting something which is pretty close to 0. It's not exactly 0, because if I were to print more digits here, but you see now this is the calculation of your gradient. So this is my first guess. I start here, and then I move here, and then within 30 iterations, I get down here. So it's not a very, how to say, efficient algorithm, as you can see. If I include this momentum here, what I'm doing now, I'm now putting in my gradient plus this momentum, which becomes a parameter. So I can tweak this parameter as I want. So I have a step size times the gradient plus this momentum, which now gives the change in the value as we discussed on the whiteboard. So if I run the calculations now with just this small change, I start at the same point, and then within roughly 14, 15 iterations, I'm just producing 0. So I just needed 14 iterations here to reach the same result which I had before. This will depend on this parameter, which I call for rho. So if I put that one to 7, let's see what happens then and rerun it. Then you will see that with 7, I actually needed more iterations. And if I put this to 1, then I have no memory of the previous step. So if I put this to 1, that means that I will get something which is just going back even worse than what I had before. So this momentum term is a parameter. It becomes a hyperparameter, which you would set before your calculations. And in this particular case here, you see now that with 0.3, I'm getting a converged solution after some fewer iterations than I had in the previous case. So this is a pretty common trick, which you would see in many, many implementations of these iterative algorithms. And you can see in this case, we need much less iterations here. Now, there's something which is called stochastic gradient descent. And stochastic gradient descent is often a method which is used in particular when you have huge dimensional spaces where you're looking after the minima. So let me just give you a quick example of a specific case where a stochastic gradient descent will often do a better job than a standard gradient descent. So if you have a function in one dimension now, a function of x here, of f of x, and your function looks much like this, has minima, it has a saddle point, etc. So this is a function where if you now start, and typically you would start at a random value. So if you start with an x0 here, then after some iterations, you would just be stuck here. And then your delta of f of x is actually equal to 0. And then your algorithm will stop. Alternatively, if you start here, then your x0 would bring you down here. But ideally, the point which you would like to reach is actually this one. Now, as I said, the energy function, which we are going to optimize as a function of different parameters, is quite often a function which is a convex function with just one global minimum. So if we then start randomly in some position in parameter space of the variables we want to optimize, we will, after some iterations, reach the global minimum. This case here is much more delicate. So what is often done then is that you slice off your points in different areas. And when you slice them up, you would do a random search in these areas. And then you would keep the value of where you find the best minimum. So that means that you would just only select a few points for X, let's say in this region, and then you could select another one, because that would bring you down here. You would then select another set of values in here, that will bring you down here. So this is a way by stochastic sampling the whole region, where you hopefully can actually be able to reach the global minimum. This is the minimum which you want to reach. So when you deal with a standard machine learning method, you will often have landscapes, and this is just a one-dimensional one. Just think of this in many dimensions, which can be pretty rugged and complex to find the minimum in. And that's where the stochastic gradient descent normally comes in as a method. We will not need that in project one, but I'm mentioning it in case you want to do the machine learning variant of project number 2. Okay, so let's go back to the Jupyter notebook. So this process is called stochastic gradient descent. And typically the way it works, if you now think of a standard gradient descent, you would then run through all the points which you have and calculate the gradient and the function you want. So this is the function you want to optimize. And when you're calculating the gradients of this function in the standard way, you would simply run over all the points and calculate the gradient. Here, on the other hand, you introduce some randomness by only taking the gradient on a subset of the data. And this is normally called mini batches. And if there are n points and the size of each mini batch is m, then there will be something like n divided by m mini batches. And that means that your gradient, suppose now you have 10 points, then the gradient would then, if you run it in the standard gradient descent way, you would run through all the 10 points. But if you have 5 of these mini batches, you would have x1, x2. These are normally shuffled randomly. And then you would have these mini batches, which now contains 2 points each. And then your gradient would just be the sum over all these batches. Now, there are reasons also for why you do that computationally. So if you have a matrix which you want to calculate the gradient of, and this matrix has, or a vector, suppose now you have a matrix which has dimensionality 100 times 100. Now, if you split this in mini batches and you're calculating the gradients, then you can have mini batches so that the matrix you're looking at each instance is only a 5 by 5 matrix. So performing typically matrix vector multiplications with a lower dimensional object saves CPU cycles compared to you running the calculation with a full matrix. So this is a consideration which often is also used when you're introducing a stochastic gradient descent. So that means that your gradient step then, if you're updating this parameter beta, is simply now given by the previous value. You have some learning rate, and then you simply then run over all these different batches. And this is something you can place yourself randomly, as you can see here. So they pick the K mini batch at random, and then you compute the gradient using the data in a mini batch here. And this is the range of the batches. This epochs is becoming a parameter. So you're actually rerunning this many times. And then at the end, your gradient is the average value over all the experiments which you run. So these are just, and the examples which you can find here are examples of the implementation of this. So I can show you a typical example on where I compare, where I'm taking the derivative of a function. So this is my data set. I'm using here an example of linear regression where I'm calculating the mean squared error. And then I have matrices here. I calculate the Hessian matrix and I run my calculation with a standard gradient descent, which is here. I have a learning rate, which is now taking as the optimal eigenvalue from the Hessian matrix. You can actually show that you can find a constraint on the learning rate. And then I perform my stochastic gradient descent. So I run over a certain number of epochs. I pick my indices randomly. So I have a subset of the values. And that means that my gradients are typically divided by the number of samples I have. And then I update with the learning rate. So if I run this example just to show you, this is the standard method with own inversion. And this is the standard gradient descent. And you will see that the stochastic gradient descent will never be exactly equal to the exact result. So this is the exact result because this is now a measurement which you make stochastically. I'm sorry. Now, there are many ways by improving the results. So one of them is to include momentum in here. So instead of having a learning rate, which is weighted with the gradients, you can now have a learning rate which is scaled so that it takes into account a previous iteration. And you can see that when we run that momentum-based approach. I'm just going to skip some of these. These are different approaches which you can see in the literature. So I'm just going to, I think I have the examples down here. Yeah, just let's leave out some of these examples here. I just wanted to mention this, but for those of you who want to do the neural network in the second project, this is something we can come back to. So this is more meant as a kind of background information. Now, one of the things I wanted to mention for you before we stop today is automatic differentiation, because you will find that useful when you calculate gradients. And automatic differentiation is an extremely useful tool, and it is not the same as a symbolic differentiation. So if you use MATLAB or Mathematica, that can set up the differentiation of a specific function for you. So just to give you an example of symbolic and the standard numerical differentiation. Why there's coming. So this is called automatic differentiation. So this is not symbolic differentiation. So just to give you an example, if you have a function like f of x, which runs like, suppose now x squared plus the exponential of x squared, look at that one. If I take the derivative of that function, then we know that the derivative will look like as f of x, and we are going to have two, no, the two disappears here. The derivative is going to be equal to x squared plus the exponential of x squared. It's going to be the derivative, and then it's going to have, just a moment, let me just rewrite it here. So it's going to have a x plus x times e of x squared divided by the square root . So there's a factor 1/2, and that gets cancelled by the 2 which we have here. And then we have another 2 of x here. So this is a derivative which you would get. So with symbolic manipulations, if you use MATLAB or you use Mathematica, they will normally give you this result here. Now, if you look at that result, if you start counting the number of floating point operations, Mathematica or MATLAB will give you an inefficient algorithm. So let's just look at that. So if you now look at the function f of x, we can define some intermediate results. So I can define a function which is a equal to x squared. And then I can define a new function which is b, which is the same as the exponential of x squared, which is the same as the exponential of a. Then I can define a new function which is c, which is a plus b. And then I can define a new function which I call d, which is the same as square root of c. And that is our f of x. If I now look at the derivatives, I can actually rewrite my derivative in terms of these functions, which are pre-calculated. So that means that what I would have then would obviously be the parameter x, which I need to put in, plus x times the variable b, and then I would divide by the variable d here. Okay. So why is this important? Now, if you take Mathematica and you ask for the derivative of this function, you would get this expression. And then you can ask Mathematica, or even if you use Python, you have symbolic Python, and symbolic Python will translate this into a Python code, or it can translate it into a C code or a Fortran code. But what it will do then, it will translate the function as it stands. Now, normally, you would calculate both the function f and the derivative more or less at the same time. So if you calculate the energy, for instance, you need the expression for the energy. You're going to need some derivatives, but you're also going to need a second derivative. So that means that if you look at these evaluations here, if I can pre-calculate this one, so this quantity which you see here, that is going to require 2 floating point operations. So if I think of a multiplication as one operation, so this has 2 flops. Okay. Now I have pre-calculated a, so I don't need to I can reuse a. So that means that if I look at this term, a has been pre-calculated. And if I think of the exponential as 1 flop, then I just have 1 flop here. Then I have an addition. So this is not, it's not true that additions, multiplications, and exponentiation take the same time, but now we are considering them as one floating point operation. Actually, the exponentiation takes more time, but now we're just treating them on an equal footing. So that means that we have 1 flop here. And finally, I'm taking the square root. So that means that finally here, the square root itself is also considered as 1 flop. So in total, I have 5 flops. Okay. Now, the function, if I were a little bit stupid and I didn't think in terms of these pre-calculating quantities, then I could just set up x times x, and then do x times x again, and then do the exponentiation, and then the square root, and plus the addition. So if I don't define this variable, then I would have to recalculate this quantity. So if you look at the derivative again, so what I have now is 1 floating point operation if I don't think now, so then I have here, I have x times x, that is 1, exponentiation, that is 1. So I have 2 operations. Then I multiply, that is 3 operations. I have an addition, that is 4 operations. So if I don't think, this would be just 4 flops. Then I have a division, which is 1 flop. And you see now I'm recalculating the function here, which is then another 5 flops. So in total here, this one gives me 10 floating point operations in the calculations of the derivative. So if I use Mathematica, and I ask Mathematica to turn these derivatives into a program, it's going to translate it as it stands without making any smart changes. But if I pre-calculate, then I can save a lot of CPU cycles. Because if you look at this derivative, on the other hand, if I look at this derivative, then I have 1 multiplication and 1 addition. So that is actually 2 flops, because everything is pre-calculated. And I divide, so that is 1 flop, division, and that's it. So D is pre-calculated. So this is three floating point operations. So if I'm a little bit smart, I can actually move down from 10 plus 5 here, if I'm calculating the function and the derivative. So that would be 15 without thinking. And then I can just move down from 5 plus 3, which is 8 floating point operations. Now, what automatic differentiation is doing is actually a repeated usage of the chain rule. That means that I am breaking my operations in terms of different smaller intermediate variables, which are easily evaluated and which I can actually calculate the derivative of. So if you now look at this function here, I have this variable b, which depends on a. So when I'm setting up the derivative of the function, I can actually now use a repeated usage of the chain rule. So symbolic manipulation is normally not what automatic differentiation is, and I don't recommend using it, because unless Mathematica or MATLAB or Symbolic Python simplify these functions considerably, you will waste a lot of floating point operations. Then it is not finite difference derivatives. So what is finite difference? So if I want to calculate the second derivative of, let's say, a function u of x, I would typically then, and this is a function which you guys have been using in calculating the kinetic energy. When you calculate the kinetic energy numerically, you would typically approximate this with some x plus a step, plus a step to the left, minus 2 times x, and this is then divided by some step size, h squared. So automatic differentiation is not doing this. It's actually a repeated, so AD, automatic differentiation, is a repeated usage of the chain rule on simple functions like x, x squared, sine and cosine, the exponential of x, etc. So let's go back to the Jupyter Notebook and look at some examples first, because this can be very useful when you want to introduce other types of trial wave functions and you're going to calculate derivatives. So for those of you who have, for instance, written a machine learning code, you have most likely encountered automatic differentiation. because that is used again and again, since you change often cost functions, you change activation functions, etc., etc. And in order for you not to hard code derivatives, which can be error prone, I know that myself, like when I've coded derivatives of trial wave functions, I had one case where I wasted a week due to a set of indices which had been interchanged for the second derivative. So I had to just interchange indices I and j, and it's so easy to make such errors. So automatic differentiation then saves you a lot of time, because there is, if you have taken a second derivative once, there is not much insight in you taking a second derivative another time, third time, and so on. So when you change trial wave functions, to use automatic differentiation gives you much more flexibility in the amount of time you actually spend on project development. Because keep in mind that your runtime, your total runtime, is not only the time your program runs, but it's also the time you spend on developing the program. So if it takes you 1 month to find accurate expression for the derivatives in paper and pencil, and then coding them takes you another, let's say, 2 weeks, and then it runs in, let's say, a week. And if you then can use automatic differentiation, which allows you to reduce this 1 month of taking the derivatives and preparing it to just a few seconds, and then it runs, it takes a little bit more time to run, I would say that is time which you can use on more useful things. Okay? So the total time of a project is not only runtime, but it is also development time plus runtime. So let's go back to the Jupyter Notebook and try to end this technicality. So this is a technicality which you can find useful in the projects. So in Python, there is a library which is called AutoGrad. But as you will see a little bit down here, this library has been replaced by JAX, J-A-X. So that incorporates automatic differentiation. So AutoGrad is a library, it exists, it runs, but it is not updated. So it has been discontinued, the project. But JAX, which also includes just-in-time compilations and many, many other features in Python, is what we would recommend using. But AutoGrad here, just to give you an example for a specific function. So here we have a sign, which has an argument x and x squared. And then you can set up the analytical gradient. But then if you use AutoGrad, you have this function which is called fgrad and fgrad, and then I compare with analytic. So fgrad here is the function which I would then include when I calculate the gradient with AutoGrad. So that would be my computed gradient. You see here that fgrad is the same as me calling this function and transferring the function f. And you can see now that this basically gives you the difference between the analytical result and the numerical result is 10 to the minus 15, which is practically 0 when we run computations. So here's another example. So I have a function here, x squared, x cubed plus 1, and then I evaluate the values. I can compare with the analytical one. Sorry. And you see basically that it gives you exactly the same result. So you can have more complicated functions. I can have a function now which depends on x1 and x2 here. Then instead of egrad, I use the grad function, and this would be typically the function which you would end up using when you have more than just one variable. And then you would simply calculate the gradient here, and you can now see the analytic comparison with the analytical solution as well. And you see that basically you get exactly the same result here. So you can have more, there are many more examples here. You can have more complicated functions where you have using the elements of the arguments directly, like this one. And you can then set up the analytical gradient and the numerical gradient. And again, you will see that the computed gradient for these different variables, they match perfectly here. So this grad function, if you want to implement that, if you want to use that, this is something which I would recommend, especially if you move into project number 2. For project number 1, you may not need to think of this because you have already done the paper and pencil exercises. But when you move into project 2, this is something you could come back to. So what I'm doing today is more to, when I wrap up this discussion of the optimization parts, I'm bringing in technicalities which you will not need immediately or may not need, but which you may find useful when you move to project number 2. And you can actually have functions which use mathematical functions from NumPy. As you can see here, you have this a function now which takes in the square root and then the sign here. And this again is an example where you get a perfect match between the analytical gradient and the numerically calculated one. I'm not going to go through all the examples. I wanted to end with an example here. So let me just go down here. There are many, many examples, but I wanted to mention to you what you could use now instead of using AutoGrad. So we normally recommend using JAX. And in this case, you would just import JAX as we have written here, JAX NumPy. And then in this case, I have a function which is given by a sum over these exponentials. And then I'm simply calculating the derivative of that function using JAX here. And in this case here, it gives me the derivatives of this specific function here. So for project number 2, it may be more relevant to use JAX, alternatively automatic differentiation if you want. Whereas in project number 1, for the optimization part, if we are wrapping up, I would recommend using scientific Python optimize. Alternatively, if you write your code in C++, I would recommend using libraries which have these functions, and there are libraries for C++, and the same for Fortran, which include these Broyden's method, the BFGS, Powell's method, etc. And alternatively, that you write your own gradient descent. For your own gradient descent, you could speed it up with momentum. These are the simplest possible approaches. And that is more than sufficient for project number 1, especially since we only have one parameter. When we move to more than one parameter, we will have to think of stochastic gradient descent and more fancier methods for also updating the learning rate. So this part concludes the optimization part. And then we are going to move next week into the calculation of statistical properties like the variance, and look at methods like there are statistical resampling methods like the bootstrap. Some of you may have heard of that. There is another method which is called the blocking method, which we will look at in more detail for the Monte Carlo calculation. And with those ingredients, you basically have everything which is needed for project number 1. Okay, so let us stop here.